Now, it's number 34 from the homework, and it was y plus 3 squared, or y plus 3 over y minus 1 squared minus 2 equals y plus 3 over y minus 1. Y plus 3 over y minus 1. And the hint I gave you yesterday was if you have something like this, x plus 1 over, say, x plus 2 all squared, it is the same thing as saying just take the numerator squared over the denominator squared. And so this is what we're going to use with this guy as our first step. So that's what I'm going to do. In fact, I'm going to rewrite it in place right here like that. I'm going to say, well, that means the same thing as taking the top squared and then taking the bottom squared. And so now we're in this type of situation where we have an equation with denominators, and I want to, what do we want to do? Remember our mantra is what?
Kill the denominators.
So, and another thing to kind of think about is this is, if I wanted to make this an easier type problem, and we had, something like this, I would say, okay, what do I multiply this entire thing by that would kill every one of these denominators?
B squared.
It would be b squared, right? Because we know that a b squared would kill that guy, and it would do it over here as well. And that would be the bare minimum of what we need to kill everybody. Well, the same thing is true here. We have something squared, nothing in the denominator here. And then we have that original thing, but now gets to the first power. And so I'm going to do the same kind of thing that I just said here, which is multiply both sides of the equation by that guy right there. And so let's do that and see what happens. Okay, so y minus 1 squared on both sides. Y minus 1 squared. Y minus 1 squared. Okay, so this guy jumps over and distributes into both of these. What is left in this first case?
Y plus 3 squared.
That's the only thing that's left on top. Y plus 3 quantity squared. Then when he jumps over, what do we have after the minus?
2 times y minus 1 squared.
2 times that quantity squared equals, okay, now what do I have on the right-hand side?
You have a y minus 1 times y plus 3.
Yes, yeah, because one of those canceled with one of those guys, and I have my what stayed in the numerator times that new thing. We could write that in either order, like you said, and that's perfectly fine. Okay, so now we have this ugly mess, and I'm looking at it, and I'm thinking maybe I could, well, I can't really factor anything out. It's not exactly a difference of squares. If I try to divide anything, I'll just kind of go back to where I came from. So that's not going to help me. So I guess what I'm thinking is maybe if I multiply these guys out, rearrange stuff, maybe that'll make my life easier. So that's what I'm going to do. What is y plus 3 squared? We got a 4.
Yeah. So
Okay.
it's the parentheses, and then you have a y. No parentheses?
Well, I'm thinking, so I know I've done 1,000 of these, and by this time, so have you. So like this is already in my head. And I'm thinking when I go first, outer, inner, last, I'm just going to go ahead and write that right now. So what happens? What is my first of these multiplications?
Oh, y squared.
Y squared. Now my outer is 3y. My inner is 3y. So put those together, and how many y's do you have?
6y.
6y. So plus 6y. And then my last multiplication gives me what?
Plus 6.
3 times.
Oh, no. 9.
There we go, plus 9. Now I'm going to go ahead and do the same thing. And so from now on, it would be helpful to, so first off, I know I'm about to multiply this guy out, so I'm going to use some brackets like this. So that I don't mess that up, which I inevitably will if I don't do this right here. And then in my brain, I see, wait, y minus 1 squared means y minus 1 times y minus 1. First gives me what?
Y squared.
Y squared. Outer and inner are the same thing. And so from the outer, we get what?
What? This is so hard for me to do mentally.
Okay, then let's not. Let's do it. Let's write it out. Y minus 1, y minus 1. Okay, so the outer gives me what?
Minus y.
And then the inner gives me?
Minus y.
The same thing, yep. And then that comes together to give me how many y's?
Minus 2y.
Minus 2 y's. Okay, good deal. Now when we do last, what do we get?
1.
Positive 1. Yes, positive 1. Okay. Now, this guy's already set up nice, so we'll just go ahead and FOIL him. And what do we get when we FOIL those guys?
Y squared minus y plus 3y is plus 2y?
Plus 2 y's, yep.
And then a minus 3.
Then the minus 3. There we go. Okay. Now what I'm seeing, now what's going through my head is this. The highest order term here is a y squared. And I'll be able to collect all the y squareds together. We have y terms and we have constant terms. And really, the only way that we know how at this point to solve an equation with we call this a quadratic, right? With something squared, something to the first power, and then a constant term. The only way we know how to do that is to set it equal to 0 and hopefully it factors. So that's what I'm going to head up. That's where I'm going to aim with this because I see, oh, I have a quadratic. The only way we know how to deal with quadratics is to set them equal to 0 and then do stuff with them. In the future, we're going to learn a different way of dealing with quadratics, but the first step is always going to be set it equal to 0.
Yeah.
Right? And that's the way it is with pretty much every polynomial equation, is we want to set that polynomial equal to 0. So at this point, when I'm looking at this, I'm thinking, okay, I'm going to have a quadratic and I need to get it equal to 0. So in other words, I need to get all the terms on one side. But right now we don't have just pure terms. We got to distribute this -2 into this mess and see what we get. So I'm going to go ahead and copy this first part, y squared plus 6y plus 9. Now when I distribute, what do I get?
Hold on, y squared plus 6y plus 9, and then you have a minus.
Wait, what's
okay, minus 2y squared, and then minus plus 4y.
Plus 4y, and then what?
Minus 2.
Minus 2, and then I'm going to copy this guy down. Okay, this guy really wants his block. Okay, buddy, one second. Let me open this for you. There you go. Take him over here. Well done. Okay, now let's get all these guys together. The way I like to do it, I like to make my y or my squared term positive. And I notice that I have a minus 2y over here. And well, actually my first thing I'm going to do is say, well, I'm going to cancel these guys. If I subtract y squared from both sides, that's gone. And so now I'm going to bring this positive 2y over here. Positive 2y squared. Okay, so that's...
Wait, where? Oh, you're bringing it over.
I added him over to this side to take care of him. So he is good. Now, I'm not going to jump too many steps at once. I just wanted to take care of those y squared terms. So now I have a 6y and a 4y on the left-hand side. So I'm going to combine those with a 10y. So those guys are gone. Keep the plus 9 here for now. Okay.
And don't you also have the -2?
Yes, I would have totally missed that. Okay, so now the 9 and the -2 are there. Okay. Now we have a plus 2y over here, plus 2y minus...
Question.
Yes.
Do you want to combine the 9 and the -2, or are we keeping those separate on purpose?
We can totally do it right now. Let's do it.
Okay.
What do we get? That gives me
7.
Plus 7.
I was wondering if there was like a purpose for
because
that.
I didn't see that too. So
okay.
You saved this whole operation. Thank you. Okay, so now we have this. Like I said, I like to have my squared term be positive. That's why I brought it over here in the first place. So that means I want to bring these guys over here.
Oh boy.
And so I'm going to have a 0. The 2y squared stays put. I subtract off the 10y, giving me what on the right-hand side?
Right hand. Right. -8.
Yes.
Y.
-8y. Okay, now I subtract off a 7 to give me a total of what over here?
-10.
So,
no, wait. Yeah.
-3 and -7, 7, 8, 9, 10. Yes.
Yeah.
-10. We are good. Don't ever trust me. Like, always double check me, because I will say, I'll be like, well, yeah, -7, -3, that's -12. Move on. And then at the end, I go, why are we not getting the right answer? Okay. So now we have this. I'm going to go ahead and erase the previous work. Okay. But let's just, actually, before I do that, let's just kind of take stock of what we've done here. We started with something and said, we have denominators, we'll kill denominators. We did that. And then we said, well, yikes, I don't know what to do with this. Maybe if I multiply it out, it'll make sense. Multiplied everything out and said, well, this is just a quadratic. If I collect like terms, maybe I'll be able to factor this guy and solve quadratics the only way I know how. And so that's where we're at now. And I'm going to go ahead and erase our previous work. And now we're going to say, all right, so this is the equation we're working with now. The original equation is equal, or it's equivalent to this, -8y -10. Now, what would you like to do to solve this guy?
Pretty sure you factor it out, right?
Yeah, what do you want to factor out?
A 2?
Let's factor out a 2. So I'm going to factor out a 2 from this whole thing. That leaves me what, and what?
Y squared -4y -5, I think.
-5. I like it. Okay. Now we're going to say, hopefully, this thing can factor. If it does, what is it going to look like?
Y.
Something like this. But yeah, what goes here?
Y.
Y's. Yep, they would have to be. Okay. Now, what are my possibilities for here and here?
I suppose 4 and 1. Or 5 and
1 and a 5. And now let's see what kind of magic we could do. The outer and the inner, we would have from the outer a 5y. The inner, we would have a 1y. Can we combine those to make a -4?
Yeah, if you do -5 plus 1.
I believe so. Now I'm just going to double check that. First gives me y squared. Outer is a -5y plus 1y gives me a -4y right there. Good. 1 and -5 give me a -5. And so, okay, now we have 2. This tells us that y could be 2 different things. Either y is equal to what or y is equal to what?
Either y is equal to -1 or y is equal to 5.
1 or 5. Okay. Now, are we done?
No.
No, we got to go back to the original equation, which had in the denominator, it was something with a y minus 1.
So if you put in a -1, it should work. And if you put in a 5, it should work.
It should work. They should both work. And so this is the answer right here. The solution set y is either -1 or it is 5. And if you really wanted to, you could plug both of those numbers back into the original equation and check that they do indeed work. But there you go. That is
Okay.
doing for that one right there.
Awesome. Thank you.
Cool. You are welcome. Okay. Are we ready to move to our topic for today?
Yes.
All right. So, unfortunately, I've avoided this as long as I possibly could, but we are going to do word problems. Everybody's favorite. I'm sorry. But honestly, what we're doing today, these types of word problems, you're going to see over and over and over again. They show up everywhere, not just in mathematics. Like, these are actually useful ones. And they all involve rates. And if you remember what I've said about calculus, calculus is all about rates. Like, it's almost entirely your first year of calculus, you're talking about nothing but rates. And let's think about why, from the little bit that we've seen about calculus, is we have some kind of function. And I said that the name of the game for year 1 is basically trying to find the slope of a function at a point. What's the slope of a function? Well, it's a rise over a run, right? And if we think about the rise and the run and a rise over a run, and if, let's say, this took the f values that are coming out, or the y values were, I don't know, a distance like miles. And if the x values were time, right? If x were time in hours, then a slope would be a rate, but in particular, it would be a speed, wouldn't it? Miles per hour, it would tell you your speed at a given time. And so we're going to be dealing with a lot of that today. No calculus involved, and you don't need to have this picture necessarily in your mind, but this is, that whole rise over run thing is central to calculus. And since we're going to be dealing with rates today, you can imagine how this type of thing you might see it in your future when you go to take calculus. And so again, getting familiar with this kind of stuff is really important. And so let's just jump right into it. I got a lot of examples I want to do. And right now, I'm just going to start with a problem. Let's do it this way. Alice. I'm going to use Alice and Bob for the names of every group of people today, because A and B make sense, right? And I don't want to have to write out Alice. So I'm going to say Alice, A, can paint a room. Can paint a room in 4 hours. Bob can paint the same room in 3 hours. How long will it take for Alice and Bob to paint the room together? That is the question. Now, what we're going to do is use a nifty little fact here. And that is that rates are additive. That is, if Alice does something at a certain rate and Bob does something at a different rate, if they work together, the rate that they do it together will be the first rate plus the second rate. And that's what we're going to be dealing with today. We're going to do this a bunch of times, and we're going to have a method, a systematic way of doing this. But one thing I wanted to say first, one second. Oh yeah, let's just think about this. Let's think about what our answer should look like. So first off, if they're working together, should it take more time or less time?
I would assume less time.
Assume less time. This is one way you could check when you get an answer and go, wait a minute. If we got to the end of this and we found that it took them 5 hours, that doesn't make sense because that would be more time than it took one of them to do it by themselves. In fact, if Bob is working by himself and he could do it in 3 hours, if he has help, then it should take less than 3 hours for them to do it together, right?
Mm-hmm.
So that's a general principle that we want to just have in our heads here, that the one who could do it the fastest, if the person who does, or in the least amount of time, then if that person has help to do a job, then it should take even less time than that one person by themselves. There's actually a question in there like that. There's a multiple choice question in your homework that does that in the abstract, and it talks about X and Y like that. But that's the principle that we're going to use here. Okay. Now, what we're going to do is we're going to come up with a rate for Alice. And now, if this were Alice drove 50 miles in 4 hours, then her rate would be, well, she's going 50 miles. I knew this was going to run out. Give me just a second. All right, I hope you could see this. So if Alice were driving 50 miles, if that were the job that she was doing, she would be going 50 miles and it would take her 4 hours, then that would be Alice's rate, right? But in this case, we don't really have a quantity, like a nice numerical quantity. It says paint a room. What is that, 7? No, we're just going to say that that is one job. Like, so she could do her one job. One job is done in 4 hours. So what about Bob? What's Bob's rate?
1/3.
1/3. He could do one job, the same job, in 3 hours. And the question is, how long will it take for them to do it together? And so what we're going to do here is just say, well, since rates are additive, right? If they're working together, then the new rate will be this. Now, here's the thing. How long will it take for, this question is asking us to find something, find some number. Let's give it a name. How about T? T is the time to do the job together, right?
Mm-hmm.
Okay, so T is the total time that it takes them to do their job together. One job per that time is that new rate. Does this all make sense, why we're setting it up like this?
Uh-huh.
Okay, yeah. And there's like 5 questions like this on your homework. That's pretty much just this principle over and over and over again, where we just construct a rate. And in that case, it's like one job and one job per the amount of time. And then we just do this. Now, I notice that we have an equation involving denominators. What do you want to do?
Oh boy. Kill them.
Kill denominator. Oh, we want to kill every denominator. What am I going to have to multiply by to kill every one of these numbers?
1 second. Let me just write it down. 4 plus 1 over 3 equals 1 over t. Oh boy. Okay. So you'll have to do multiply it by 4 and 3 and t.
And t. There we go. And we're not going to try to be tricky and say, well, it's 12t, because that's not going to help us out, right? Like even visually, that would just make my life harder. If I keep it factored out like that, right, on both sides, I can see, well, this will make my life easier. Let's do the right-hand side first. When I multiply those guys together, what's left over?
Well, 4 times 3.
4 times 3. There we go. 4 times 3. I'm not going to jump ahead. Maybe I want to keep it like that. I don't know. I'm not going to write it as 12. But the t's cancel. Okay, so now this guy's got to jump over and hit this guy and this guy. When he hits this guy, what's left over?
3 times t.
3t. And then when he jumps over and hits him, what's left over?
4t.
4t. There we go. Okay, now we have 3t plus 4t. How many t's is that?
7t.
7 t's. Let's just do it that way. 7t equals, now it's starting to look like I could go ahead and multiply that guy out. 4 times 3 is 12. And so t equals what?
T equals 12 over 7.
12 over 7. Now, let's just stop and think. I believe that's the answer. Okay, and let's see if it makes sense. We said that it should be less than the fastest time, right? Otherwise, it doesn't make any sense. And so is 12 sevenths less than 3? I think so. Let me just
yes.
Is 12 sevenths less than 3? If it is, then it must be the case that 12 is less than 3 times 7. I just multiplied both sides by 7. It must be the case that 12 is less than 21. Yeah, okay. Since 12 is less than 21, 12 is less than 3 times 7. Therefore, 12 sevenths is indeed less than 3. This makes sense. That is how long it would take them to do the job together. In the answers, and I realize I didn't like text you the answers for this last section. I realized that this morning, but I'll do
okay,
that.
I got my book.
Oh, you do? Okay, good. Okay,
yeah, we got it.
Excellent. So in the answers for this, they write them as improper fractions. This would be written as, what would it be? What's 12? 1 and some 7.
And then 4 5 7s, I think.
Something like that, right? That's how it would be written. I don't care.
Yeah.
Like that's for you to check your work. Like good. That's the amount of time. What I do care about, hi buddy. What I am going to care about for this whole section is that you write the units. What is this? This isn't 12 sevenths of a jelly bean. This is what?
Hours.
Hours. Okay. That is how many hours it takes them to do the job together. Does that make sense?
Yeah.
Okay, let's move on. A slight variation on this kind of problem is the following. A swimming pool can be filled using a pipe or a hose or both. Oh, wait, you have your book. Do you have your book with you right now?
Uh-huh.
You do? Okay, then I'm not going to waste my time writing these on the board. We are going to do problem number 6 on page 273. Okay, so a swimming pool can be filled using a pipe or a hose or both. I love drawing pictures. So I'm
273.
Page 273. Yes.
Found it.
Okay. So we are doing number 6 from 273.
Yep.
can be filled using a pipe or a hose. Here's the pipe, here's the hose, or it could be used doing both, okay? All right, now it says that using the pipe alone, it takes 12 hours. Using both, it takes 8 4/7 hours. I hate when they do that. How long does it take to using the hose alone? Okay, so what they're asking for, let's go ahead and identify what they're asking for. How long does it take for just the hose? Okay, what's the rate for the pipe? The pipe can do one job in how long?
12 hours.
Okay, so then what's the rate?
1/12.
1/12 is the rate that the pipe works. It could do one job in 12 hours. Okay, so what about the hose? What's the rate for the hose?
Oh boy.
We don't know. I mean, that's the answer. That is what we're looking for, right? Like that's my variable, right? Is how long does it take to use the hose alone? So let's introduce a variable here. In fact, let's call it X. Let's just say X is the time for the hose to do the job. So what would the rate for the hose be?
Sorry. I guess it would be both minus P.
Whoa.
I don't know. Wait, what?
Yes, that's ultimately what we're getting at. But I'm saying if I told you that this was 5.
Oh,
5
1/X.
1/X, yeah. I
Sorry.
wasn't very clear. I'm kind of beating around the bush, but I wanted to use our variable to describe this. And this is a good way of doing this. You identify the variable you're looking for. And in this sense, I mean, with what we're doing here, I know that we're going to be, just like you anticipated, adding these rates together. But I wanted my variable, the thing I'm trying to find, to show up in it. Now it says that it takes 8 4/7 hours. Yikes. Okay, first off, let's go ahead and convert this. 8 4/7 means 8 plus 4/7. So if I need a common denominator, that common denominator's got to be 7. So if I multiply 8 by 7 and divide it by 7, remember this little trick that I've done before, right? I just say, oh, I'll just do this.
Mm-hmm.
So what is 8 times 7?
I
don't know this one.
I don't know.
I don't know this one. 7 times 7 is 49.
56.
6. Okay. So 56/7 plus 4/7 is how many sevenths? 60.
60.
So 60/7 is the time it takes for both of them to do the job together. So remember what we did before? We said like the time it takes Alice plus the time it takes Bob is equal to the time it takes both of them to do that.
Mm-hmm.
Well, that's what I'm going to use that same info right here. I'm going to say, okay, the time it takes one thing to do something, or that rate, plus the rate, which is 1 over the time that it takes for the other thing, is equal to 1 over the time it takes both things. Only now I'm going to write that as a fraction, 60/7. And so that's what we're looking at right here. And let's just stop and see if this makes sense. This is the rate for the pipe to do it. This is the rate for the hose to do it. Add those rates together and we get a new rate. And that rate is one job divided by the amount of time it takes to do that job. I think that sounds good. First thing I want to do right now is when I divide by a fraction, what's an easier way of dividing by a fraction? How can I rewrite that?
Multiplying by a reciprocal.
Okay, so this whole thing turns into what? 1 times what?
1 times 7/60.
7/60. So I'm just going to rewrite that whole thing as 7/60. That should make my life a little bit easier. 7/60. Okay. So now I have an equation involving denominators. What do I want to do?
Kill the denominators.
Kill the denominators. So what do I need to multiply to do that?
Oh boy. Multiply by 12. Multiply by x.
Yep.
And multiply by 60.
Go. 12x and 60. So let's do the right-hand side first. Looks like the 60s cancel, and what's left over?
12 times x times 7.
12 times x times 7. Okay. Now, on the left-hand side, this guy comes in. What cancels and what's left over?
60x is left over.
And then that comes over and leaves what?
12 times 60.
12 times 60. Now you could see why I said we will need a calculator for today, because this is ridiculous to try to do without that. So do you have your calculator with you? Because mine is being used as a camera right now.
Yeah.
Okay, so what is 12 times 60?
720.
You said 720, 720?
Yeah.
Okay. Now, what is 12 times 7? I should know this one.
84.
84. Okay, 84x. Okay. So now what do you want to do?
I guess subtract 60x from both sides.
And that leaves me with what?
24.
Is it 24? Yeah, 24. There we go, 24x. And now what do we do?
X. Divide both sides by 24.
Well, and what do we get when we do that?
30.
It's 30. Nice. Okay, so let's stop and think if this makes sense. It says it takes this thing, the hose by itself takes 30 watts. I didn't write it down here. 30 what?
Hours.
Hours.
I think.
No, it takes 30 hours to do. Okay. And so doing them together, it took 8 something. Okay. I mean, there's not much more analysis to do. Just wanted to make sure that this didn't come out to be something crazy, you know. It takes a long time to do this. It takes much less time to do it with a pipe. And so we don't get that much of a benefit. We only get, it cuts it down to 8 and some odd hours. And yeah, because this thing's pretty slow if it takes 30 hours to do it. So, okay, this sounds good. But I didn't get anything wacky. I didn't get like, you know, -5 hours. That would be bad. So I believe this. This sounds good. With these types of things, and you will have quite a few, well, yeah, you'll have a few of these. They tell you that a job can be done in a certain amount of time. And so that means we want to set up a rate, one job for some amount of time. And they say that the job can be done by somebody else in a different amount of time. And then they say either what is the total amount of time that it takes, but this is the setup for these types of things. Sometimes this one, the combined time, will be your unknown. Sometimes it'll be one of these guys that's your unknown, and that's what we saw right here. But in every case, your stuff should look generally like this. Now, the only thing, and this isn't in any of your homeworks, these are all pretty much there. These are all simple. It says that one job can be done in this time, one job can be done in this time. How long does it take to do one job? And that's what they give you. But just for future reference, if it were a setup like that, like our original one, Alice does it in 4 hours, Bob does it in 3 hours. How long does it take them to do it? Well, what if they said, how long would it take them to paint 3 rooms? Well, it's then in that case, we wouldn't be talking about, well, one of the, this is their rate, this is their rate. And then we're not asking how long it takes to do one job. We would be asking how long it takes them to do 3 jobs. Similarly, if at the beginning they said, Alice can paint 2 rooms in 4 hours, well, then our rate wouldn't be 1/4, it would be 2/4. So that's not going to show up in your homework, but just so you know, like that you have to use your brain. Don't think that in every case, it's just 1/time, 1/time, 1/time. That is not always going to be true. You have to kind of use your brain and think, what is the rate with my given information? Okay, ready to move on?
Yeah.
Okay, so didn't really need the picture for that. The pictures will come in handy here in a minute, but at first we don't really need them. Now, what we're about to do, everything else in this section is their distance, rate, and time problems. And so, just like before, a rate was something over something else. And when we're talking about speed, we have your rate is your distance over time. It could be miles per hour, could be kilometers per second, or meters per second, or whatever, right? But that's generally the idea, is that we have this. This equation is going to be basically our governing equation for everything that we do with these types of problems. Now, how do we solve for t? Let's say I told you, I gave you this equation right here and said, Kayla, solve for t. Tell me what I would do.
You would.
I have an equation involving denominators.
Yeah, you would cancel the denominator. Multiply both sides by t.
Okay, so I multiply both sides by t. And I get, okay, I multiply this side by t and I multiply this side by t. And now that's gone. And I'm left with d r t. Now what do I do to get t by itself?
Divide by r.
Divide by r, okay. Okay, so sometimes we'll be using this equation like this. Sometimes we'll want to rearrange it and use it like this. Sometimes we'll want to rearrange it yet again and do it like this. And I'm sure that, and there's probably something else we could do here, but we're going to be using this pretty much with every one of these questions. So it's just something to know, right? A rate is defined by a distance over a time. And so if you know 2 rates and some distances, we could find time. If you know your rate and your time, you could find distance, right? But in other words, every one of these, depending on what you're looking for, if you're trying to find a rate, this is how you find it. If you're trying to find a time, this is how you find it. And if you wanted to find a distance, that is how you find it. So let's put this into practice. We are going to do number 270, from page 274, we're going to be looking at number 10. Okay, it says the speed of a stream is 3 kilometers per hour. A boat travels 4 kilometers upstream in the same time it takes to travel 10 kilometers downstream. Whoa, okay, I don't know about you, but I need a picture here. So I'm gonna draw a stream, okay? That's my stream, and it is moving in a certain direction, and it says that the speed of the stream is 3 kilometers per hour. Okay, so I'm gonna go ahead and say it's moving right at a rate of 3 kilometers per hour. That is the rate of the stream. Right, and that makes sense. Distance divided by time is a rate, and it's moving this way in 3 kilometers per hour. Okay, now it says a boat travels 4 kilometers upstream. So upstream is upstream with or against the current?
Against.
Against the current. So it goes 4 kilometers upstream. So it goes in this direction. It's 4 kilometers upstream. It says in the same amount of time that it takes to travel 10 kilometers downstream. So I'm going to do this right here. 10 kilometers downstream. Okay, now that makes sense. Just kind of looking at what they've given me here. If my boat is traveling at a given speed, like if I'm going against the current, I should go a smaller distance than when I'm going with the current. Okay, that's what it tells me to do. Now it says, what is the speed of the boat in still water? So what I'm going to do is write a variable down. I'm going to say S is the speed of the boat. Speed of boat in still water. Okay, so S is the speed of the boat in still water. So let's look at this. What we're going to do, and we need, and now one thing it says, and this is something to notice, it says in the same amount of time, right? It says a boat travels 4 kilometers upstream in the same amount of time it takes to travel that far downstream. So in other words, whatever that time is, we don't know what the time is, but we don't really need to, because this is the thing that's going to help us relate something together. That's why I like having these equations right here. And so this is the trick. When you're given something like this, when it says the same amount of time, what I'm going to think is, well, this is, since time is equal to distance over rate, right? Then we know that the distance, in fact, we're going to call this trip right here going upstream, we're going to call that trip 1. And I'm going to say that trip, the first distance that it traveled at the first rate that it traveled, D1 over R1 is equal to that time. But in the same way, this second trip, right, that distance and at its rate, whatever it happens to be, is also equal to that same exact amount of time. So D2 over R2. The only thing that remains is to figure, because we know the distance traveled in the first trip, that was given, right? That's 4 kilometers. So in other words, what I've just set up here is we know that this guy has to equal this guy right here. Pretty much all of the rest of the questions involve some kind of thing like this. They tell you that something can be done in the same amount of time, or that something can be done in the same amount of distance, or something has the same rate, but then they give you these other things. And the trick is to say, well, if this happens in this amount of time, I don't need to know what amount of time it is. The idea here is that I could relate these guys together. Does that make sense?
Mm-hmm.
Okay, so what is the, so let's fill in what blanks we have right here. What is the distance of the first trip, of the upstream trip?
4 kilometers.
4 kilometers, okay, over rate 1. Now, what is the distance of the second trip?
I'm sorry. Okay.
10 kilometers.
10 kilometers over rate 2. Now, here's the tricky part. The rate here, the rate for the first trip, we're going, well, remember, we're trying to find the speed of the boat, and I've even given it a letter name, right? So the rate of the first trip is going to be, well, however fast the boat's going, but that is going to do something to the speed. It's going to change the speed. Is it going to make the overall speed greater or less if it's going against it?
Hold on. I'm sorry. What?
So here's the thing. We're in our boat. And on the first trip, we're heading in this direction. So here's our boat. We're heading in that direction. And the boat moves at a certain speed, but the water's coming against us. So is that going to slow us down or speed us up?
Slow us down.
It's going to slow us down by that many kilometers per hour, right? So we could say then the rate that I'm doing when I'm going in that direction is whatever that speed is, right? So my rate for trip 1 is going to be whatever my speed is, but minus 3 kilometers per hour. Does that make sense? It's slower, right? Like whatever the speed would have been, but minus 3, so it's actually slower. And so that's what I'm going to do right here. I'm going to say rate 1 is whatever the speed of the boat is minus 3 kilometers per hour. So this rate 1 is going to be S minus 3. So then what about rate 2? When we're going in the direction of the current, what would that be? We want S to be in there, but then what's going to happen to it?
Wouldn't be S plus 3.
Exactly, right? Because if the water were still, it would be going at whatever S is, but we have a boost of 3, and so it would be S plus 3 kilometers per hour. So S plus 3 for the return trip, or for the trip with the current. I'm just going to replace that right here and say, okay, S plus 3, like that. So now, looking at this, I have an equation. I have one unknown, okay? That's the only thing I'm trying to solve for is S, right? And that's the whole goal right here. That's why I wrote it down, because I wanted to see that. That's what I'm looking for. One equation, one unknown, I should be able to solve it. So I have an equation involving denominators. What do I need to do?
Fill the denominators.
Fill the denominators. So what do I do to do that? What do I need to multiply by?
S minus 3 and S plus 3.
There we go. And so I'm going to do that to both sides. Right? On the left-hand side, something cancels, and what's left over?
Hold on. Okay. On the right-hand side, it's 4 times S plus 3, and then on the left, it's 10 times S minus 3.
There we go. Okay. I'm going to go ahead and rewrite that up here. In fact, I'm going to go ahead and distribute this guy in. What do I get on the left-hand side when I distribute in the 10?
10S minus 30.
There we go. And on the right-hand side?
4S plus 12.
4S plus 12, okay. Now, okay, what do you want to do?
Add 30 to both sides and then subtract 4s from both sides.
Okay, I'm going to subtract 4s. That leaves me a 10 and 6s. You said add 30, 4 and 2. So 4 and 2, I believe. Please check my math.
Yeah, that's right.
Now, what do I do?
Divide by 6.
Okay, and what do I get?
S equals 42 divided by 6. 7.
7?
Yeah.
7 what? Jelly beans? Kitty cats?
Kilometers per hour, isn't it?
Kilometers per hour. And that is the answer. The speed of the boat in still water is 7 kilometers per hour. Now, one thing, and I do this all the time. I will mix these up and think, oh, okay, yeah, it's going with the current, so we need to subtract off the amount of the current, which is exactly wrong. Or the speed is going against the current, and so we need to add it on. And I just messed those up. And what would have happened? Let's think about this. Earlier, we had 10 and we had 4. And if I had mixed these up, we would have said it was the speed minus and then the speed plus like this. And we would have multiplied, we would have ended up with 10s plus 30. And we would have ended up with 4s minus 12, like that. And then moving on, we would have had 6s equals minus 42. My point is, if you get to this point and you end up with, in the end, s equals negative 7 kilometers per hour, it should tell you that you did something wrong. You don't have a negative speed, right? That should tell you that, oh, I mixed these up. I did this part wrong. And so, does that make sense what I'm saying?
Mm-hmm.
Right? So it's with these questions, it's super easy to mix these up and do the adding and the subtracting of the rates the wrong way. And when you do it, it's pretty obvious that, oh, that's what I've done. So like if you end up with a negative answer and you know it should be a positive answer, that's probably what you did. You just said, oh, wait, I should have added instead of subtracted and vice versa. So, okay. Any questions with that one?
No.
No? Okay. So you'll have a few like that. We're going to move along and do this one. The speed, okay, so this is 12, number 12. The speed of train A is 12 kilometers per hour slower than the speed of train B. It travels this in the same time, so this is, right now my ears perk up and I see they're not giving me an actual time. They're telling me that something's going to happen in some amount of time. Something else is going to happen in that same amount of time. And so I'm thinking, okay, I want to use this in that similar way. So we're going to have something like this. Time is for the first case, but the same time is going to work for the second case. And so I'm already thinking, all right, it's probably going to work out something like this. So let's get some info down. The same time that it takes train B to travel that far. So what I'm going to do with these and what I suggest to do with most of these types of problems is make a team. I'm going to say, okay, here's for train A, here's for train B. The information, and remember, each one of these involves 3 variables. There's a rate, a distance, and a time. In this case, they're giving us a distance and a rate for each one of these. So I'm going to go ahead and say, okay, the rate and the distance is like that. And I'm going to say, okay, the distance is the easy one to get. How far does train A travel?
What? 12 kilometers per hour. Wait, no, sorry, 230 kilometers.
230 kilometers is the distance that it traveled. Okay. What about train B?
290 kilometers.
290 kilometers. Okay. Now the rates here. Now this is where it gets tricky. It says the speed of train A is that much slower than the speed of train B. So what I'm going to do is this. Let S equal the speed of train B. Because it says A is something slower, or twice as much as, or 4 times that of B. And so B is like the pure thing. And that's what I'm going to let S equal the speed of B. And so then it says that A is 12 kilometers per hour slower. So then what is the rate for A?
S minus 12.
Oh. S minus. That makes sense, right? And I'm just looking at this. I'm thinking, okay, if S were, say, 32, then the rate for B would be 32. The rate for A, well, 32 minus 12, it would be 20. And so, yes, it would be slower than that. Okay, cool. I feel good about this. And so now, here we go. And again, I started off by noticing which one of these I wanted to use here. You know, it's like, wait, we have time. Time is the thing that is the same in both cases. So I could relate these two things together by time, and I don't need to know what it is. I don't need to know if it's 50 hours or 20 hours. I could just say, well, forget about it. It could be any amount of time. I'm going to put these guys together here. And so let's do that. D2 over R2, or we could think about that as the distance that B travels over the rate of B equal to the distance that A travels over the rate of A. Well, what is that? What is the distance that B travels?
290.
290. And what's the rate at which it travels?
S.
S. Okay, what about this other fraction? What should it be?
230 over S minus 12.
Okay, now what do you want to do?
Cancel the denominators. So multiply each side by S minus 12 and S.
S minus 12 and S. Okay, so on the right-hand side, I'm sorry, left-hand side, the S's cancel, and I get 290 times S minus 12 equals, those cancel, and I get 230S. Okay, now I'm not gonna, I have more examples I want to do, and we're running way out of time. So I'm not gonna, we're not gonna finish this guy up, but just something to notice is that I'm going to check that I'm on the right track by doing this. And it's the same kind of principle that I was talking about a second ago. So I could see that when I subtract 230 over to that side, I end up with a positive number. I'll bring this over to this side and I'll have a positive number. And so S should be a positive number. So I feel confident that I set this up the right way. But if I had messed this up, right, if I had done either S plus 12 here, or I screwed up and said, you know, at the very beginning of this and did like S minus 12 on this one, we would have ended up with a negative number. And that would be a clue that, oh, I did my adding with the rates the wrong way. Interesting thing that we're doing here, you'll notice it's kind of the same principles that we're adding rates, right? Just like we were doing in the beginning. The very beginning of what we were doing is using this principle that I could take a rate or a speed and then add or subtract another speed to or from it. Okay, so you good with this? You feel good?
Mm-hmm.
Okay, so, oh man, that's a tough one. Yeah, and you're gonna need, I got a couple. Okay, so. All right, now, 16, enough money to commute. I don't want to worry about that. Okay, so number 26. The average speed is defined as, you see 3 lines like that for instead of an equals, when you see 3 for an equal sign, it means we are defining this to be the total distance traveled over the total time it took to travel it. That's what average speed is. And so number 26 says Wayne drove 3 hours on a freeway at a certain speed. Then he drove 10 miles in the city at a different speed. What was his average speed? Now here's the thing. In order to get average speed, we need to know 2 things. 1, the total distance traveled and the total time. So those are the 2 things we are looking for. And so what I'm going to do is say, okay, then D is going to be the total distance Wayne traveled. Big T is going to be the total time it took. Okay, so we have 2 trips basically that we're going to analyze here. It says 3 hours on a freeway at 55 miles per hour. Okay, so trip 1 is on the freeway. He drove at 55 miles per hour. And the time, in fact, I'm going to call it T1 here. The time for trip 1, T1, was 3 hours. Okay, so that's the information we have. We know the time it took, and we know his rate, right? So that's rate 1 right there. Now, later on, it said he then drove 10 miles in the city at 35 miles per hour. Okay, so he's driving at a rate of 35 miles per hour. So that's, I'm going to call that rate 2. It's the second rate, his second speed. And he drove a total of 10 miles. So this distance right here is 10 miles. So let's see. In order to get the total distance, I'm going to need 2 things. I'm going to need to know the distance of trip 1, which I'm going to call D1, plus the distance of trip 2, which I'm going to call D2. The total time it took is going to be the time that it took him to drive in the first trip, which we already have, and then the time that it took for T2. Does that make sense, what I'm doing here? It's over total time is going to be the distance in the first trip plus the distance in the second trip divided by the time for the first trip and the time for the second trip. We have T1, right? It told us it took 3 hours. So we're done right there. In fact, I'm going to go ahead and write it down. I'm going to say, we know that that first one was 3 hours. We're almost there. Now, do we have any, have they just given us a distance? You then drove.
Yes.
Yeah, what is that distance? And I think it's in the second trip.
10 miles?
Say again?
Is it 10 miles?
10 miles, right. He drove a total distance of 10 miles, and that's in the second trip. So then D2 is 10 miles. Okay, so we're almost there. So then all that we need then to figure out this problem is to find out how long did he drive in the first trip? What was the total distance he drove in the first trip? D1, how far was that? And then we need to know how long did he drive in the second trip? Those are the two things we need to find out. And what's nice, and I have them still written up here, this is all related by these guys right here. If I need to know the time for the second trip, and I know the rate and the distance of the second trip, well, it's right here, isn't it? I could just say the total time that I'm looking for, in other words, T2, is the distance that he drove in that trip and the rate at which he drove during that trip, which is what? What was it? What was his distance traveled in the second trip?
10 miles.
Oh, 10 miles. Divided by what rate did he drive at? At what rate did he drive in the second trip?
35 miles an hour.
35 miles per hour. Now, interesting thing to note is we could kind of check ourselves here. We're looking for a time, right? That time should be in hours. And we took 10 miles and divided by miles per hour. And what do you know? Miles divided by miles per hour is the same thing as multiplying by the reciprocal, hours per mile. The miles cancel and we're left with a quantity here that is just in hours, which we expect. That's what it should happen. It's what should happen. So 10 divided by 35, I'm just going to call it 10 over 35 hours. That is the total time it took him to drive the 10 miles right there. That is the second time. So I'm going to go ahead and put that up here. Still looking for D1. We don't know the distance. 3 plus whatever this is, 10 over 35. And in the end here, we're going to have a bunch of fractions and fractions. For all of these questions, use your calculator. We're not interested in, are you there? Hello?
I'm here.
Disappeared.
Yeah, my Wi-Fi is being really, really bad.
Okay.
And everything's super, super laggy. So I'm trying to preserve my bandwidth by
Okay,
keeping
cool.
my video off.
Okay, cool. Are you following along though?
Yes.
Okay, cool.
I think so.
So all I'm saying is like with these problems, right? I'm not worried about like, you're going to get 10 over 35 and you're going to plug that into there. Just use your calculator. I'm not concerned about any of that. The last thing we need to do is find out the distance of the first one, right? How far did Alexander or whatever his name was, how far did he drive in given this information? Well, we know that rate times time is distance, right? So then the first rate times the first time is equal to that distance in the first trip. And so the rate was what? What was his speed on the first trip?
55 miles an hour.
55 miles per hour times how long did he drive?
3 hours.
3 hours. And you'll notice, hey, that also hours in the denominator cancels with hours in the numerator, and you're left with a quantity that's just miles. And whatever 3 times 55 is, I don't know, 15, and then another 15, so it's 16, 165 miles. 165 Okay, so that is my D1 right there. And I'm going to finally replace that right here and say, okay, 165 miles on the first trip plus the 10 miles from the second trip is the total distance that Bob traveled. He drove for 3 hours in the first trip plus for 10/35ths of an hour in the second trip. And that's the total time that Bob drove. And so if I take the total distance over the total time, I get what we have defined as the average speed. That is your answer right there. If you want, you could leave it like that. You could plug it into a calculator. You could keep it as like you could make it into a nice mixed fraction. I don't care, but this is what we're looking for right there. Good to go?
Yeah.
Okay. There's one more thing she could paddle out on Lincoln back. Okay, yeah, you're gonna need to know this. I'm sorry, but yeah, we got to do this one because this one's tough. All right. Last one we're gonna do. This is number 16. I have not been writing the numbers up here, but whatever. 16. Alice has just enough money to rent a canoe for 1.5 hours. Okay, 1.5 hours. How long or how far out on a lake can she paddle and return on time if she paddles out at one speed and paddles back at a different speed? So I have to draw this out. I'm going to say, okay, she's going to go out some distance. We'll call it D. And she's going to go out at a rate of, we'll call this R1, and we'll say 2 kilometers an hour. Okay, so she's going out at R1 is 2 kilometers per hour. She goes back at a different rate. R2 is 4 kilometers per hour. 4 kilometers per hour. And now it says, and this is where it's so tricky. Now, one thing to notice about this, it doesn't say that she does, you might think, oh, she does the first trip. He fell. I'm sorry. Hey, you're fine. You're fine, buddy. You're doing good. You're doing great. Watch Grover. Okay. You think, oh, okay, the first trip is done in the same amount of time as the second trip. Like that's when I was doing this one earlier, that's just immediately what I thought, because that's what we had been doing for this whole all these homework problems up until now. You say, okay, there's 2 trips. It doesn't give me the time. It's done in the same amount of time. No, that doesn't make any sense in this case. If you think about it, because if she's paddling out at a certain speed and goes a certain distance, paddles back at a different speed and goes the same distance, that cannot take the same amount of time. So what I'm going to do is split up the total time into 2 different times. In other words, I'm going to say big T is the total time, which we know what that is. The total time has to be 1.5 hours. But there's the time it takes in trip 1 and the time it takes in trip 2. So we're going to say, okay, she paddles out for a certain amount of time, T1, we don't know what it is. And she paddles back in a different amount of time, T2, we don't know what it is. So T1, we don't know. T2, we don't know. But we do know that that total time, the time for trip 1 and the time for trip 2, add together to give me the total time, which we know is 1.5 hours, because that's what they gave us. So this, I have to go over this one because this one is super tricky, because you will just assume like, oh, with all these other ones I've done, it's the same amount of time in both trips. And so I'm going to do this same kind of trick that I did before, and you would be wrong. So in this case, it's the distance that's the same, right? And so we don't know what distance is. They didn't tell us whatever it is. In fact, is that what we're looking for? She says, how far out on a lake can she paddle? That's what we're looking for. But in this case, right, we have, this is kind of like a two-part problem. We're going to say, all right, we don't know what that distance is, but in both cases, it was the same. So in other words, D is rate 1 times T1 is the same thing as rate.
I don't know. I'm so sorry. You're sick.
T2. Okay, so in other words, R2 times T2 is equal to R1 times T1. What of these do we already have up on the board that we could fill in, like actual numbers?
I'm having a really hard time tracking because the connection is so terrible.
Okay, I'm sorry.
No, it's my fault.
It's
on my end.
It's Comcast or whoever's fault. So
yeah,
I'm gonna finish this up because this is the last little bit you're gonna need for homework and stuff like that. This will be posted later today, and you'll have all weekend stuff so you could review this stuff. So
okay.
Okay. So we know they have given us the second rate, which is 4 kilometers per hour. So I'm going to replace R2 with 4 kilometers per hour times T2. The rate in the first trip we're calling R1 is they've given us is 2 kilometers per hour. So I'm going to say 2 times whatever the trip was for T1. Now here's the problem. I have 2 unknowns, but I could write one in terms of the other. And that's what I'm going to do. I'm going to say, well, hold up. Since we know that T2 plus T1 is equal to 1.5, I could say T2 is equal to 1.5 minus T1. And now I've taken an equation. And there's another principle we've talked about a bunch of times. I have 2 unknowns. I need 2 equations to solve them. Hell, if you wanted to, you could turn these 2 equations into a matrix and solve that way, but we don't need to do that. We're going to say, I have 2 unknowns, T1 and T2. I have 2 equations. This one, 4T2 equals 2T1, and T1 plus T2 equals 1.5, so I could substitute if I want, which is what I'm going to do. I'll get T2 by itself, and that's T2 equals 1.5 minus T1. And so I'm going to replace T2 with that variable right there. 1.5 minus T1 equals 2T1. Now I have 1 equation and 1 unknown, and I should be able to solve that. Please help me out here. What is 4 times 1.5?
4 times... Whoa, hold up. My calculator is being weird. Okay, 4 times 1.5 is 4 times 1.5. 6.
It is 6. Okay, 6 minus 4 times T1 equals 2T1. And so now what I'm going to do is add 4T1 to both sides. That gives me 6 equals 6T1. And so I could solve for T1 by dividing both sides by 6. And I get 1 is equal to T1. So let's put this back into context here. What just happened? We found that she rode out for 1 hour. Okay, so T1 is equal to 1 hour. Now we have enough info to answer the problem. We don't need to go back and find T2 actually, but we can if we wanted to, because who knows, like that might actually help us with a later problem or something, I don't know. But we could say then T2, since T2 is 1.5 minus T1, then that's 1.5 minus 1. T2 is just 0.5 hours. And that makes sense because the total trip we know had to be 1.5 hours. And so 1 hour one way, 0.5 hours the other way. She should just be able to do it. And now if we wanted, we could use either of this info to find D. Because we know that D is equal, the distance is equal to the rate times the time. I like using T1 because it's a 1. It should be nice and easy. I could say, okay, then T1 times rate 1 is equal to the distance. R1 times T1 is equal to that total distance. R1 is 1 hour. No, R1 is 2 kilometers per hour times 1 hour. Hours cancel. 2 times 1 is 2 kilometers is the total distance she traveled. And we could see that if we had used the other equation, R2 times T2 equals D, R2 times T2 equals D, we would have ended up with the exact same thing, as we should. 4 kilometers per hour times 0.5 hours does indeed give me 2 kilometers was the total distance traveled. So the answer for number 16 would be D equals 2, not jelly beans, not sandwiches, kilometers. I want to see units, please. Does that make sense?
Yes.
This is fast and furious, and I kept like rambling at the end and saying the same thing over and over again like I do. But that's the idea with these. Like I personally, I have to draw pictures, even if they don't help me out. Like I almost messed this one up when I was working it out earlier because I got into the habit of thinking, oh, they haven't given me a time, so I'm just going to set these two things equal to it. And then I got lucky and said, wait a second, hold it. Draw this out. Wait, she's traveling the same distance. It can't be the same time. Okay, there's something else going on. And so drawing stuff out will help you out 9 times out of 10. Sometimes it won't, like when I drew the hose and the pipe, that did nothing for me. But especially with distance and time problems, work out a nice little system. I usually do something like this for distances. I put, bars because I think about like a ruler, and so that helps me think about distance. For rates, I draw little arrows because I've taken physics and that's what you do for speed, but have a little system that you've worked out and it will help you out with all of these. So let's write down your homework. I'm going to go ahead and erase this stuff. Okay, so we did get to that one. We did not talk about that one. That one is a doozy. So it is going to be, homework. Chapter 6, section 7. This is on page 273 to 275. 273 up to 5. Numbers 1 through 29 odd.